All right, well, thanks everyone for jumping back in here. Um, I figured my first thought was we'd just go on a tour of our Nix build system. But when I started asking people a little bit about what they wanted to know, some things that were a little bit lower down in the conceptual tree came up. So I figured I would just try to fit together some concepts that I think everyone's heard of these things, but maybe people aren't quite sure how they fit together or how they work. And if I just go over a few of these things, then I think a lot of the build system will become much more clear very quickly. So I called it everything you wanted to know about Nix, but we're afraid to ask. Of course, it's not everything you wanted to know because I'll have a slide about topics we could do in the future towards the end. Can everyone hear me okay?
Yeah, you're coming through great.
Okay, so we'll jump in first into what do Nix expressions look like? What do expressions look like in the Nix language? We'll try to breeze through that because I think everyone's mostly familiar with that, but I'll try to address a couple of things that people have said are a little bit confusing. We'll spend some time talking about derivations, which is how Nix actually builds things. We'll do a little bit of theory, and then I'll actually show a derivation that doesn't use the standard environment for Nix packages, but just the very basic primitives that Nix gives us for derivations. We'll talk about package sets. So Nix packages is a package set, but we also have like our Plow GHC packages is a package set. We'll talk about overlays because that is primarily how we build stuff on top of Nix packages and customize it for our own build system. Okay, so we'll jump right into the syntax a little bit. First, everybody's seeing strings in Nix. You can quote any string typed expression into a string using very similar syntax to bash. If you see an unquoted path or an unquoted URL, that's also a string. So you can just imagine there being quotes around these, but Nix doesn't make you put the quotes in. List, it's real simple syntax, but something that trips people up. There's no commas or other separators inside of a list. So if you have some non-atomic expression, you need to put parentheses around it if it's one element of the list, so you don't have commas to break up your elements. Is that all clear so far?
Yep.
So attribute sets are just sets of key value pairs, but this is really the data structure in Nix. Basically everything you work with in Nix will be an attribute set. You can just write them out with curly braces and equal signs and each. So here's something that gets people sometimes about Nix. Semicolons, for the most part, they just end bindings. So you put a semicolon at the end of a binding in a let, you put a semicolon at the end of a binding in an attribute set. The only other place where you put a semicolon is in a couple of scoping keywords that we'll talk about a little bit later, but you don't have to actually end every top level expression with a semicolon. So this will throw errors at people sometimes that they put a semicolon at the end of their Nix file and they didn't need one because it was just the top level expression. But something like this is just essentially constructing a set of named value pairs. You can also put the rec keyword in front of your open brace, and what that will do is that will also make each of the names in scope for the values everywhere else. So here, developer again is Edward.Amson, but instead of saying Edward.Amson TeleTech.net, I just quote that that value into the email string. The Lambda syntax also, it's deceptively simple and people are looking for something a little bit more, I think sometimes. It's just your argument, colon, and then the body expression. Any questions so far? If you have questions, I can't see any of you, so if you have questions, you have to unmute and talk.
Nope.
Okay. So Nix has pattern matching, and this is more often the form you'll see of writing functions. The pattern matching is mostly just on attribute sets. It's a little bit subtle, and this trips people up sometimes. If you just write out a set with just comma separated names, that's an exact pattern. So Nix will expect as an input to this Lambda a set with these names and only these names. So if you are missing any, or if there are names in that set which are not in the pattern, Nix will generate an error. It'll be a runtime error. There's no static checking in Nix. It's JavaScript for build systems. But so if you get an error about matching, maybe you were expecting to pattern match on just some attributes. So if you want to let yourself have extra arguments that you're not matching on, you just put an ellipsis at the end of your pattern after a final comment.
And presumably if you pass in a string or something to this, it'll have some error too, right?
Yeah. It'll say something like got a string, but a set was expected or something like that.
Okay.
Any other questions? Okay, so another thing, this will be familiar to most people in Haskell. You can name your pattern so you can get the whole input to the Lambda as a binding and not just the individual variables from the pattern, just with the @ sign. So it's exactly Haskell's named pattern syntax. The question mark syntax that you see used quite a bit is actually a way of specifying a default value. So just like the ellipsis lets you say, I want to match on these, but it's okay if there's others. The question mark says, I want to match on these, but if you don't have them, just use this value instead. The neat thing is that all of the arguments in all of the matching variables in the pattern are in scope for the defaults everywhere. So in this case, I expect an attribute set with 2 attributes, developer and email, but if I don't pass either of them, I'll get Scott Murphy at plowtech.net. If I just pass developer, let's say if I change just developer to edward.amsden, then email would default to edward.amsden at plowtech.net.
So is there like an internal, like, so is it like an implicit mutually recursive set in the pattern match? Is that like, do they distinguish those in terms of like its dynamic type tag or whatever?
Sorry, like, you broke up a little bit. I couldn't quite hear the question.
Well, it seems like these are the mutually recursive attribute sets in the pattern match. So I'm curious if they distinguish those or not, like at runtime.
I don't know. So the mutual recursion is just that on the names of the attribute set that get matched, you can use them in the pattern default. So this is, remember, this whole thing is the argument side of a Lambda. So this is going to be matched against your input. And the question marks are just the default values if you don't get that particular input.
Right, so there's almost like a little program that gets run on your arguments before you actually call it.
Right. Yes, and you will see this leverage, I would say, well past the point of abuse. Probably in our build system, certainly inside Nix packages, you'll see this leverage well past the point of abuse, where you almost have to read the pattern and figure out all the expression, because you can put an arbitrary Nix expression to the right hand side of this question mark. So you'll definitely see this, like a lot of times there will be like Boolean inputs to a Lambda, and then for other inputs you'll have whole if then else statements to the right of the question mark based on that Boolean input. So your default for one will change based on what flag you pass in for another one. It gets kind of crazy. If used judiciously, it's a nice feature, but it does, like, a lot of people just write their code in the pattern. And then I have seen literally like all the code is in the pattern, and then just one of the defaulted parameters winds up being the output of the Lambda. That does happen. Any other questions?
So if I pass in like a Boolean for the developer instead of string, will that be like a runtime error as well?
Yes, Nix will not quote non-string things into a string. There
Okay.
are functions. There are functions to convert from ints to strings, booleans to strings, whatever. But I said it was the JavaScript of build systems that's a little bit unfair, because it's a lot saner about typecasting, as in it doesn't. So it
Python
does.
and build systems.
Sorry.
We can say Python and build systems.
Yeah, that's probably closer.
So are these quoted things just a binding name, or are they actually expressions? This like $ parent developer close.
You can also have an arbitrary Nix expression in there. It's very not. You usually won't, but usually it'll just be a variable, or it might be attribute selection, like a chain of attribute selections, like this dot this dot this.
Okay.
Anybody else before we go on? Okay. Nix has let bindings. Again, it's just a name equals an expression, semicolon. Let bindings, just like in Haskell, they're mutually recursive. And Nix is lazy. So you can build infinitely nested or infinitely mutually recursive attribute sets, and Nix is just fine with them. And again, this is something that's leveraged probably well past the point of abuse in Nix packages, and also in our own Nix code here at Plow. So in this case, we have a set that references both itself. So if you get a set attribute of a set, you get the same set back, and you could chain as many of those as you wanted. And then another set, which is defined down here. So we're using this mutual recursion. We're also defining mutually recursive sets. So there's a whole knot being tied here. So I could write out an arbitrary chain of a sets and another sets, except I don't self-reference another set inside itself. So after another set, I have to write a set. Any questions about let bindings or laziness or infinitely nested attribute sets?
So is like the dot sort of like the force thing that's like forcing an evaluation there? Or like a set dot another set, so it's gonna like evaluate one level.
So
like what does it do in terms of evaluate? Does it only evaluate, now you have like the property names, but like none of the values are looked at until you would
right
the value?
Right. So if you I'm pretty sure if you dot a set, then you're evaluating just what names it has. And so you're forcing the set as far as what names does it have.
And there's nothing dynamic about the names. It's like all
Oh no,
Sure.
there is. We'll see that.
Oh, okay.
So I got asked about inherit, which sounds object oriented, but isn't really. Inherit is just take these names from the current scope and stick them in the attribute set. So this is the same thing as before, except I left out the name attribute. But this just inherits the set from the scope, which is defined by our let binding here, and the another set, and just makes them attributes of this attribute set, the set that we're defining. And then again, in another set, we inherit set. So
inherit takes like a list of things, and it's like that first inherit is just, it's just like it's equivalent to 2 separate inherit statements.
yes, yeah, that and a single element inherit statement is equivalent to just name equals name, right? So this is equivalent to a set equals a set. But because without the rec keyword, these aren't attribute sets aren't mutually recursive blocks. You're just defining key value pairs. A set on the left-hand side is just the name in the set, and a set on the right-hand side comes from the containing scope. So this is just a shorthand for that pattern of a set equals a set. Does that make sense?
Yep.
Okay. And then going the other direction, and this is a little bit easier.
Terrible, naming that they call that inherit. It took.
Oh no, yeah,
it's
no,
so awful.
no, it suggests object orientation, and it's nothing of the kind. It'd be better to call it capture or freeze or something like that. But
Yeah.
going the other direction, and this actually more or less makes sense, even naming wise. The with keyword takes a expression that evaluates to an attribute set, takes all the names from the attribute set and puts them in scope. So down here where I have, at the bottom where I have the with keyword, we have an expression that, you know, after all the dotting just evaluates to a set, but now X is in scope, valued as it is in a set. So this whole thing would evaluate to 1.
So it's sort of like an open or an import or something like that.
It's almost exactly, I mean, it's dynamically typed, but it's almost exactly open from ML. Yeah, it takes a record and puts all the record names in scope. There's a lot of hate for with in the Nix packages maintainer community, and it does get abused, but I think a lot of, like, there's people who are almost ideological, like, don't use with in your Nix packages definitions, and I think that's going a little too far. So as inquired about, you can actually dynamically select attributes from a set. So attribute names are just strings, so you can dot any string expression, and in particular you can quote into a string. So in this case, the 2 values that won't error that you could pass into which set are the empty string and another, just as a very contrived example. So you can say, so this would, if you pass in the empty string, this would evaluate to a set dot x. And if you passed in another, then this would evaluate to a set dot another set dot x. So yes, there is dynamic selection from attribute sets.
So there's dynamic selection in terms of like which attribute you get, but is there dynamic creation? Like, could I create a record that has, like, could I, instead of, so this is like in the in part or in the property projection or whatever, but what about like if you said a set equals in that definition of a set, could I like dump a there, which is sort of similar, like where the left of the equals has some dynamic thing in there.
I don't know if you can sort of dynamically name things within the construction syntax, but there is a built-in list to, it's called list to attrs, list to ATTRS, that essentially takes some key value pairs. Of course, Nix doesn't have pairs, so it takes a list of attribute sets, each of which has a name and a value attribute, and turns that into an attribute set. So you can dynamically name attribute sets, just it's a little bit more involved than just quoting on the left-hand side.
So it's kind of like a library function more than like a syntax thing.
It is, but it's, I mean, it's built into the language. It's not in librangle. I don't know how you would write it if it wasn't built in, because there's no other way that I know of to dynamically name attributes of a set.
Thanks.
Okay, so just to recap a little bit, put everything together. A good way to think of attribute sets is just as scopes packed up. Think of inherit as selecting assignments from the current scope and putting them into an attribute set, and with as taking an attribute set and putting the assignments from that attribute set in scope in the sub expression for width. We're going to go on and talk about derivations next. Does anyone have any questions about the expression language of Nix before we go on and talk about derivations? Speak up with questions if you got them. All right. So we're going to talk about derivations, which are the way in which Nix builds software. A Nix expression can evaluate to a derivation, and if it does, the derivation will be written to the Nix store and can be built. So what is a derivation? At the Nix language level, Nix will try to treat a attribute set as a derivation if it has the name type bound to the string derivation. That's all it takes for Nix to try to treat this value as a derivation. So if you load it in the REPL, it'll try to pretty print it as a derivation. If you run Nix instantiate on a Nix expression and it evaluates to an attribute set that has this binding, then it will try to generate a derivation in the Nix store from that. At the Nix store level, derivations are just the files ending in DRV that you'll see. What Nix build will say, I'm building this .drv. That just means it's actually running the build process that's encoded in that .drv file.
Is the DRV a binary or is it like text? What's the format of that?
It is a certain format of text. We'll see that.
Say that again. I didn't catch that.
It is very specifically formatted text, and we will see that. Okay. Yeah, we'll actually take a look inside of the DRV file in all of its horror and glory. So the Nix instantiate command is the plumbing command that takes a Nix expression and puts a .drv evaluates it and puts a .drv in the store. Nix instantiate is sort of a plumbing command. If you're just building stuff with Nix, you usually don't use it. You do use it pretty often in debugging. Nix build is essentially just Nix instantiate followed by an invocation of the Nix store command, which builds the derivation. So Nix build is basically just a wraparound those two commands. So in the Nix language, at the Nix language level, like we said, we're building a record with this attribute, but it needs some other things too. And so there's a built-in constructor in the Nix language called derivation. Here's an example, one that won't actually build, but it will write a .drv to the Nix store. Just if you try to build .drv, it won't work. These 3 parameters to derivation are all that's strictly necessary. You have to name your derivation. You have to tell it what builder to run. And you have to tell it what system the derivation is valid on. This example is actually from Nix build, which I'll reference at the end, and is a pretty good way if you want to just go from 0 to really, really competent in Nix and you have a lot of time. It's much more in depth even than the Nix documentation tends to be, so it's very helpful. So in this case, this one won't build for a couple of reasons. One is that this isn't, this is a builder is actually a path to a builder. This isn't really a valid path in any temporary directory. It should either be like / or a reference to something in the Nix store. And there's no system that you can run Nix on where it will check what system it's on and it will say my system. Suppose we could invent one, but usually this would be like x86-64 Linux or x86-64 Darwin if you're on Mac. If we look at the .drv, it sort of got cut off with the last one here, but this is what it looks like. This is actually a supposedly interlanguage format for serializing expressions called aterm. And I haven't actually seen it used outside of Nix. But there's a particular expression structure that Nix serializes into aterm format and then writes out to the .drv file. And you can see it's mostly just like name value pairs. The Nix command, which is actually a bunch of commands bundled up with an executable, has a pretty printer Nix show derivation. If we run that on our derivation, this is what we get. Notice in particular, there's an output path, which is already calculated when the derivation is written. So if you have the derivation, you already know where in the Nix store its output is going to be, even if you haven't built it yet. So a Nix build prints that output path, all it's doing is just printing this out. And then this environment down here, under builder, we see arguments and environment. That's what will get passed to the builder executable. So in this case, we're not passing any arguments, but in the environment, we see that the builder has access to its own name, to the name of the derivation, to the output path, which is important because the builder is actually what's going to write stuff into the store, and also to the system. We go back and look at this derivation command. Actually, all of the inputs that we give to the derivation primitive go directly across and become environment variables for the builder. Any questions so far?
So are these environment? These are like there's literally like a $ builder or something that's passed to like whatever.
So if your builder was a shell script or an executable, you'd be able to just get builder from the environment, and the arguments are literally their command line arguments. I'm going to show an example of a really simple derivation whose only dependency on Nix packages is just to get a hold of bash without a lot of bootstrapping, where we'll see we'll see this a little bit better. So we'll see all three. We'll see the path to the builder executable, we'll see the arguments, and we'll see the environment, and will actually just be a pretty simplified version of what the Nix standard environment does for its derivations.
Is there any kind of like special casing for Nix expressions themselves, or would you have to like re-invoke Nix as a builder or something? If you wanted to like I don't know.
You really don't use low-level. So this is all still like, so this is the result of something from the Nix link. But remember, this is a Nix expression. So all of that, anytime there's a reference to something in the Nix store that's then going to get pulled in and evaluated inside Nix, Nix will take care of evaluating and building that so that it can be referenced. And that's called, there's a name for that pattern. It's called import from derivation. In private build systems, it gets used a lot, most especially we use that to pin Nix packages. So Nix actually downloads Nix packages to the Nix store and then references it from there. We do that in our build system. In Nix packages itself, it's really frowned upon, both because they sort of want it to be a closed world thing where everything in Nix packages is in the Git repository, and also because it is, it slows down evaluation because you have to actually go out, run a Nix build, fetch stuff as part of evaluation. So, but that pattern that you're referencing is called import from derivation, and the high-level Nix language does handle it automatically. Does that answer your question?
Yeah, I think so.
Okay.
It gives me a better idea.
Okay. So, like I said, the .drv files are just serialized expressions in A-term format. The pretty printer that comes with Nix is just Nix show derivation. There's another one from Gabriel Gonzalez has the Nix derivation package on package, and that has an executable in the package called pretty derivation that will pretty print in a slightly different way, but both are much more readable than trying to read the A-term serialization. So we'll jump over to a terminal here, and we'll actually take a look at a simple derivation. So the first thing you'll notice is that this is actually a lambda with a pattern match. Basically, anytime we write derivations in Nix, not every single time, but most of the time, we put them in a lambda and get whatever dependencies and configuration options we need through the lambda. This sort of modularizes it, and the Nix infrastructure has a lot of support for this pattern. So, but we're calling the derivation function here. We have the name and the builder and the system. But here we're getting the builder from, we're passing in bash. And so I said Nix doesn't cast. There's one exception to that. If you have a derivation and it has an output path, which any derivation constructed with the derivation function will, then that output path will be a string, and Nix will substitute in that string when you're asking for a string instead of an attribute set. So I can take bash and treat it as a string, which will just be the output path of the bash derivation, and then underneath that output path just bin bash. So there's my builder. And
so if something is a derivation, it has to be attribute set with that derivation.
Yes.
Does that happen?
Yes. So as an argument, I'm actually passing in, so notice I say /, which means is relative to the Nix expression. So I have, I have simple builder.sh in my directory here. And what Nix will do is it will actually copy simple builder.sh to the Nix store and then substitute, sort of silently substitute in the path to it in the Nix store, so that your derivation has access to it without going back and having access to your source directory. Built-ins.current system just gives you the system that your derivations would be checked against on the local system. So in my case, it would be just the string x86-64 Linux. So our derivation file is a Lambda, so it has a couple dependencies. We're going to see more about how you fill in those dependencies later on. But for now, this is the file we're actually going to import. And this just essentially says, fill in those dependencies from Nix packages. So if I load that file into so it says added one variable, so it actually, if you load something into the Nix REPL, it tries to evaluate it to a attribute set, and then it sort of does a whiff into your top level scope in the REPL. And so simple derivation is now, so if I just look at simple derivation, it just says, hey, it's a derivation. Here's the path to the derivation in the store. So we can go take a look at that, and there's that awful. So just by the act of evaluating that, even in the REPL, we introduced that derivation into the store.
So it looks like that load in the REPL gave the arguments to the Lambda in that.
Yes. So this is another sneaky thing, is that if a Nix command expects the expression it's getting back to be an attribute set, but it gets back a function, it will try calling that function with the empty set. So you can have arguments. So you can have arguments as long as they're all defaulted. There's a further thing where you can, for a lot of commands, you can specify arguments. So like if you call Nix build, it will do this thing where it will just pass the empty set, but you can also specify arguments, named arguments to go in that input attribute set on the command line. But yes, good catch. So from the REPL, I can actually ask it to build this derivation. Okay, so now we have an output path. Let's take a look at what's in that builder script that we're passing as an argument to bash. So we're just taking the environment variable message and echoing it to the output path. If we look at Nix here, notice all I did was just inherit message in the arguments derivation, which means whatever message is bound to here will get into that environment variable for the bash script. So by default, the message is Nix is cool. So what do we expect to see if we take a look at this store path? Nix is cool.
So a Nix store path could either be a directory or just a plain file then?
Yes, it can be either one.
And that depends on whatever builder you're using, I guess, whatever that happens to do to that path, right?
Right. You can also, remember I mentioned that, so if we look for where simple builder is mentioned in simplebuilder.sh is mentioned up here in the, this actually just got copied to the Nix store, which means it got, this is its SHA-256 hash, and then it just got copied to the Nix store in the act of evaluating. So there was a local path that we were mentioning in a derivation. It just got copied to the Nix store rather than writing out that path, because once the derivation's in the store, we expect to be able to build it independently of what happens outside the store. So we don't want to reference back to the source directory. It gets copied into the store, and then the only thing the derivation you can see is stuff inside the store.
So what's its resolution like? So clearly if it has a relative path, it'll put that. What if you just pass in some absolute path? Does it like check whether it's already /Nix store, and then if it isn't, then it copies it? But if it is a Nix store, does it just use it? Or
if it,
I don't know anybody would actually hard code such a thing, but.
Well, no, but you remember you are passing an absolute path in effect here where we quoted bash, because it just uses the output path here. So what it will actually do is go and see if there's a derivation with that output path. And so if the output path doesn't already exist, it'll try to build that derivation to generate that output path before it goes on.
Yeah, I was thinking of the /simple builder below that though.
Right. So that's again, almost always you're putting in relative paths, and those paths are relative to the only, I don't even know if you could just explicitly write out an absolute path. I assume you could. I also assume that you would get confused by the results.
Yeah, probably.
Good. All right, so we made a simple derivation and we got a file back. And again, we used all of the ways of getting information into the derivation. We named the builder, we just used bash. We passed one argument, which was the bash script that we wanted to run. And then we actually, again, because all the arguments to the derivation function wind up as in that. So if I do, instead of cat, if I do if I show that derivation, we look down at n, there's 5 things named in the input, and there's 5 things in the environment that gets passed to the script. So the script could reference any one of these names just as an environment variable.
And where did we bash? I just don't remember.
We got bash from Nix packages. So the actual file that we evaluated was this one. So we just imported a pinned Nix packages. This has a bunch of stuff to grab a particular version of Nix packages from Git. And then call package, we're actually going to see more about call package a little later, but essentially it just looks at the Lambda and fills in the arguments of the Lambda from the PKG's set.
Great.
Okay. All right. Does anyone else have any questions? All right.
Can you go back to the
terminal?
Yeah.
Okay. What's up?
So here, when you're saying that you fill, for example, like you fill the bash attribute would be the ones that from the packages.
Yes.
Does it? So it determines that by the name of the attribute.
Yes.
Right?
So there's call package is very, very magic. I could do a lightning talk just on how package sets and call package works but yes, it's just by the name of the attribute in the pattern. So I pattern match on the name bash here. So in the set, in the PKG set, whatever derivation is assigned to that name in the PKG set is what I'll get here.
So it must be derivation. So it couldn't be just like for example, maybe like a boolean or like a string. It must be derivation for the tool.
No. It doesn't actually have to be. It just has to be defined in that PKG set. The only reason I need it to be a derivation is because I treat it like one by quoting it as part of a path.
Okay.
Okay. If this was a string, actually, this would still evaluate properly because it just gets quoted into a string. And here, I mean, here I defaulted it, right? But here I have another parameter that is, it's a string, right? So usually everything with a few utility exceptions, everything in a package set will be a derivation, but that's, we're going to talk about package sets a little bit more here in just a minute, but usually, yes, you're expecting it to be a derivation, but there's nothing in Nix or even in the mechanism of call package that says this must be a derivation.
Okay.
And in fact, it's, you know, because the way you're packaging stuff into derivations, usually you're writing a lambda and then writing a derivation based on the parameters of that lambda. Usually it's both the dependencies and configurations. And usually the way you tell the difference is that the dependencies are just left as required parameters and all the configurations are defaulted somehow. Does that, but again, all of this is just convention.
Okay.
Any other questions? Any other questions about derivations at all? We're going to go on and talk about package sets. So package sets are just sets of derivations. Nix packages is a set of derivations and other package sets and other sets of package sets and package sets all the way down. Our Plow GHC packages set is a package set. So like I said, it's an attribute set whose values are derivations. It's not strictly necessary that all the values be derivations, but that's sort of what you're expecting when you get something from a package set. Nix packages is the canonical set. Getting a hold of Nix packages, usually if you have Nix on your system, you have some default Nix packages that was updated sometime in the past, somewhere on your system that you can get a hold of. So the import keyword just means take this file path and evaluate the contents of the file as a Nix expression here. So import Nix packages just pulls in the angle brackets, just actually means that it looks up the path in an environment variable. But it says just, you know, take this file path and read it as a Nix expression. And then the Nix packages set takes an attribute set argument before it gives you back the set of packages, and that's where you pass in configuration and other things. So by default, you can just pass in the empty set. More commonly in a development scenario, what you're going to want to do is what we call pinning Nix packages. There's a good discussion of it on the NixOS wiki under FAQ/pinning Nix packages. But it's going to look something like this, where you have an import and then you're using either built-ins.fetchget or built-ins.fetchTarball. And what these will do is just when they evaluate, they will go grab whatever is specified by their arguments and put it in the Nix store and then return the Nix store path. So we can import the file path that gets returned by fetchget. That will be a path in the Nix store. And then again, pass the empty attribute set to it. And this particular hash here, I actually didn't remember to update the name, but that won't matter. That's just the name it will give it in the store. This particular hash here is actually the latest as of whenever I was last working on the slide of the release-1903 branch. So it's the latest stable release branch of Nix packages. So that's how you get a hold of the massive Nix expression that is Nix packages. Within Nix packages and basically everywhere else is Nix, as we already saw, you usually treat packages as functions. So you list off everything that you're going to need to build your derivation as a pattern match. And then
I noticed that in the pattern matches, you don't have the ... for like extra attributes. So it seems like it's a little smart about what it decides to pass in.
yes, so specifically again, call package, like I said, call package is very magic. And I could do a lightning talk just on how it works. And I only figured out today the sort of dark magic behind how it does this. Because you would think, oh, it's just sort of a self-apply, right? So if I call pkgs.call package, that's equivalent to just my package applied to pkgs, but it's not, because it does some smarts so that you don't trip up on the extra arguments thing in a pattern match. But yes, again, that's a good catch. It's something that I wondered about until today as I was rooting around trying to build actually some stuff for the overlay stuff that we'll talk about, and figured out what magic that they do. But yeah, so you just write out a pattern match for the things you're going to need, both dependencies and also configuration stuff. So Shulhi, to your question earlier about derivations, this argument, stdn, standard n, isn't a derivation. It's actually a little library of functions for working on a little library of functions for creating nice derivations for building stuff. And most everything in Nix packages is built using the stuff in standard end. So standard end isn't a derivation, but you'll call package will still give it to you because it's part of the Nix packages set. So the standard environment, the function you'll usually use is called mk derivation. And you can think of this as like a really, really smart constructor wrapping around the low-level built-in derivation function. Only in this case, there's two required parameters. One, again, is the name of your derivation, and the path to the source. Fetch URL is another built-in thing that will grab something and stick it in the Nix store. So in this case, we'd be grabbing some tarball from a URL, making sure the hash matches, putting it in the Nix store, and then the source would just wind up being the path to it in the Nix store. And what standard end will actually do is it has a standardized build script that does the standard GNU dance step to try to build something. So it will unpack. So if you give it a local directory as a source, then it will just copy that directory to the Nix store. If you give it a reference to some tarball or a zip file or whatever, it will try to unpack it. It will then run, it will look for a /configure script and run that with appropriate standard options so that the prefix is the output path, and it looks for other things in the right places. It will then run make to build. It'll run make check and check the build result. It will run make install, and since it gave the prefix to configure, it expects make install to put all the stuff in the output path of the derivation. And then it will run some sort of Nix specific fixes, things like checking dynamic linker paths and interpreter paths and shell scripts, and making sure those point to the Nix store and not to random places on the system. So that's why you're not directly passing, at least by default, you're not directly passing the builder args environment stuff that we saw for derivations, because it has sort of a standard set that it gives. And it actually, you still get, though, that anything you write down in this input, you still have access to as an environment variable from your builder. I don't go into it in this talk, but all of these phases are overridable. Actually, the list of phases itself is overridable. So you can, that builder script is so generic that just by changing environment variables, you can inject entire new code from your Nix expression into the builder script and build things different ways. And this is how, for example, we do Haskell builds, or we do Rust builds, or we build something that's packaged with Node instead of configure and make, or we build something that's packaged with CMake instead of configure and make. We just override these phases, and we can actually just provide shell scripts as strings in our Nix source. Any questions about that before we go on?
Yeah, the phases, I mean, the instantly fixed phase are in different environments than the other phases, right? I mean, when you install the build product, it's in the final, I mean, directory where the product is built, right? The check is in like a local environment.
So everything here is happening in a temporary directory inside sort of like a change root environment, so it doesn't have access to anything else, and in the output path. So there's actually two check phases. There's one check that runs in the temporary directory when you're building, and then there's a phase called install check that runs checks again, but in the output path.
Awesome.
So does that answer your question?
Yeah, sure.
Okay. So the other thing to know about the make derivation function is that you notice up until now we didn't mention any of these dependencies except in the Lambda, which meant we weren't using them. But we want our configure script, especially, but also our make and everything else, to have access to the things from these derivations, because, well, they're dependencies. So make derivation takes a parameter called build inputs, which is just a list of derivations that will get built first, and then the binaries from those derivations will be available on the path inside the build script. So if configure is looking for a specific executable, it will find it on the path. The headers will be visible again, so configure can find, make sure it can find the headers. When you run make, it will pass the right flags from configure, so it uses those headers. And the libraries will be visible, so you can statically or dynamically link against those libraries. Anyone have any more questions about make derivation? Just because make derivation is used everywhere, and I can just pull up an example if I need to. I don't have an example of it in the slides, but it's something I'm pretty sure anyone who's dug into Nix has seen already, and I just wanted to point out this is the way we really make derivations in practice. We don't usually call the derivation built-in function. Any questions? All right. So the other side of this is, as we've already had a couple of questions about, we put all our dependencies into a pattern match in a Lambda, and we need to resolve those dependencies. The standard way to do this is you have a package set that has the dependencies and also has a function called call package, which will go and fill in those dependencies. It also takes an extra attribute set as a parameter so that you can either override dependencies that it's passing by supplying them yourself, or supply other arguments like configuration arguments. So we'll take a look at one case where you would actually put something in there. So here we have, oh no, that didn't use call package in that case. The override function is basically just saying, take this derivation, pretend like you're redoing call package, but pass these parameters. So I could have put this, I could put this right here, and it would change that message input to, remember, if we look at it has this message parameter, so I can change that to plow is cool, and then that would be what would get passed in as the message variable to that build script, and we wind up with that text in our output instead of Nix is cool. Any questions about that so far? There is another little bit of magic for convenience in call package, which is if it gets a string, it will try to treat it as a file path and try to import that file path and read the package function from that.
I have a question, just sort of about packages, which is
Yes.
like, how do I tell what's in a package?
Meaning what's in it? Meaning like,
well, like for instance, like in Nix packages, there's like a function called Haskell packages, and like there's like all kinds of things in it.
right. The if you want to just sort of look it over, the best thing to do is to get into the Nix REPL. So if I do, I'm in the wrong directory. So if I do, so if I want to look at what's in Haskell packages, there's a built-in function for Nix actor names that will give you back all the names of an attribute set as a list.
Oh, that's handy.
So I can just do, and oh, of course. And there's everything that's in Nix packages.haskell packages. Which
Oh man, that's huge. That's so nice.
And then, okay, so I want to know what version of zip conduit do I have? So now that I know that zip conduit is in there, just to pick one at random. And actually here it throws an error because there's some exception logic built in where packages can be marked broken. So rather than evaluate it to a derivation, when I try to evaluate this, again, Nix is lazy, so you can have little undefined or error bombs. And this one, I picked one at random, but it has a little error bomb saying this is marked broken right now, so it won't actually try to build it unless you change your configuration.
Yeah, but I've ran into that. This is marked broken a lot.
Yes,
it is terrible.
It's the set of Haskell packages in Nix packages is rather poorly maintained because they're trying to do what Stackage does and maintain one big global set of packages with blessed versions, but they're trying to do that for all a package instead of a blessed set of packages. And they want to have just one instead of an ongoing set of LTS versions. So Haskell.nix takes advantage of the fact that Nix is a programmatic package manager and actually lets you handle the fact that, oh goodness, there's different versions of packages on package. You might want a different version. So that's but yeah, so that's the best way to just sort of explore through a set. The only thing is the REPL, I would say, is about the toddler stage of software maturity, which is to say it can do what you ask, but sometimes it might not do what you ask and just lay down and throw a fit instead, and you have to put it in timeout and come back to it. So, and it's at really random, and so you'd be like, well, I just wanted, why can't I can see inside 3 levels of attribute set, but not 4 in this particular case. And no, I'm just going to lay down and have a fit, and you have to kill the REPL and come back at it a different way. But that's
still like a lot better than how I was doing it, because I was trying to go in through Nix instantiate and then doing a bunch of evals, and so like this.
Yeah, right. Nix instantiate is more robust, but a lot more painful to use. Does that answer your question?
Definitely.
Okay. So just to recap, a package set is a set of primarily derivations. Packages are functions from derivations to dependencies, and also any sort of configuration to a derivation for the software that you're packaging. Call package takes a package that is a function and produces a derivation by supplying the dependencies from the package set. And so call package tells us how to get stuff out of a package set. Overlays are sort of the main way that we get things into a package set. So we'll talk about those next. Any more questions about package sets, packages, call package, the Nix standard environment, any of those things before we go on? Anybody? All right. So overlays are the way that Nix, a very general mechanism that Nix provides to sort of override a package set. And you might want to do this because you want to change the version of something that's included, change some configuration or something about how something's built, or because you want to add things to a package set that aren't included by default. So basically our entire build system is just a bunch of overlays on top of Nix packages. The thing that gets people about overlays, and the reason it gets people is not because nobody understands recursion and functional knot tying, but because the Nix documentation does everything it can to avoid saying recursion or tying the knot, and thus making it instantly clear, tries to gesture and waffle at this. At least that was my experience of trying to learn about it. Maybe they've improved the documentation. So this is not the actual code that applies overlays to a package set, but this should be a full-dar, but conceptually this is what happens. This double slash is a preferential set union. So it unions 2 attribute sets, preferring values from the left in case of a collision. That's all it does. Sorry, preferring values from the right. Preferred values from the left, we never get any. So what's going on here is that an overlay, if we're applying each overlay from a list of overlays, each overlay takes 2 arguments, which we call self and super. The first argument that we call self is the result of this whole fold. So it's a reference to the set that we get by applying all the overlays. The second one is the result of applying all overlays prior to this one in the overlay, or actually probably after this one, since it's a full bar. So I just wanted to put this up here because this is really everything that's going on, and we can come back to this slide if things aren't clear a little later. But I feel like everyone needs to see this in order to, and just sort of have this in mind in order to understand what we're actually doing with overlays. So again, the self is the result of the whole thing, and super is the result of everything up to that point in the fold. So to define an overlay, like we said, an overlay is just a function with two arguments. Now, it's not an attribute set with two elements, it's actually two lambdas. So you could give other names, and sometimes people just stick underscores here because they don't care about one or both of these. But by convention, it's self and super, and it's passed by order, not by named parameters in an attribute set. And again, the first argument is the package set after all the overlays are applied, including the one that you're defining. And what you want to do with this one is you want to get your dependencies from it. If you need to explicitly specify dependencies, you want to get your standard environment from it if you need to explicitly mention standard environment. If you're calling a package, you want to call package from this so that your dependencies get fulfilled from the result of applying all the overlays. This means in particular that in terms of what dependencies are available, the order in which overlays are applied doesn't matter. So why do we even have super? Super allows us to sort of break the knot so that we can override a package based on what's already in the package set without introducing an ill-founded recursion. So for super, it does matter the order because the overrides that you apply using super will get done in the order of the overlays. So a couple of examples. If you're just adding a package, you want to define that element, that new element, to be self.callPackage and then your package expression. And again, you want to use self so that you get the dependencies after all the overlays are applied. Any questions so far? We're going to do a little example where we actually build up a package set from almost nothing just by applying overlays. When you are specifying a dependency, you use self. So here, this is something that you'll do sometimes, not very often, but sometimes. So in this case, like I mentioned before, this override function is just, I want to go back and do over my call package for VLC, but change some of those extra arguments that I passed. So VLC expects live Blu-ray as a dependency, but I don't want to use the live Blu-ray that ships with Nix packages. I want to use make MKV because it can pretend to be live Blu-ray. So make MKV I'll get from self because it's a dependency. I'm not overriding or redefining make MKV, but because I'm redefining VLC but using the value of VLC that's already in the package set, I'm going to get it from super. If I got this from self, this would be self-referential. Is the distinction between those two arguments and the reason for them, is that clear to anyone? Does anyone have any questions?
Can you say that? Can you say that one more time?
Sure. The dependency comes from self so that I get the result of the dependency after all of the overlays are applied. I'm redefining the VLC attribute here, but using the VLC attribute that was already in the package set as part of that definition, because I just want to diff it, I want to change it slightly. I'm getting that original VLC attribute from super so that this definition is not self-referential, because if I got it from self, then that would refer, I would be saying VLC equals VLC with some, applying an extra function, but there'd be no basis to the recursion.
Okay.
So what would that do in that case? Would it just
Nix, I mean, obviously, Nix is Turing complete, so you could actually wind up in an infinite evaluation loop. The more likely thing, though, is Nix does black holing, just like GHC does, so it will complain that it encountered infinite recursion and error out.
Yeah, that's I get that a lot. Okay, so in this dependency, is this the okay? So self. What is self in this case? Is self the same as super, but after all the derivations, or is
No,
it
so self is the result of the whole fold of all the overlays to the package set. So each overlay has access to the result of applying all the overlays.
Okay. Oh, that's
Because
interesting.
that's the final. So that means that if you wherever you introduce or override a dependency, so if I introduce or override bash anywhere in my set of overlays,
Yeah.
all the overlays that mention self.bash will get that version of bash.
Okay, that makes sense.
And
I
this,
see.
again,
I was wondering how that happened, because that's
Yeah.
like a weird, like that just, yeah, that makes a lot of sense. Okay.
Okay.
I was trying to fight that. All right.
Okay. But that's how that happens. Okay, so like I said, we're gonna actually see an example of sort of building a package set just from some overlays. So like I said, I could do a whole lightning talk on how call package works and how package sets are defined. That would be a whole separate talk and would run very long. But this preamble in my let is essentially just getting me a package set that's equipped with call package, but not really anything else, and is equipped with call package and a way to apply overlays to that package set. And then here I'm introducing a bunch, instead of just defining the package set, I put a bunch of identifiers into a set that I can load into Nix REPL. So if I come over here, our own set. So it says added 8 variables, so that's all the variables in this set here. The scope with overlays function just takes a list of overlays and applies them to this empty scope or empty package set that I defined up here. And so it's empty, but it's not actually empty. It just doesn't have any derivations in it. It only has call package and a couple other bookkeeping things in it. So if I do with just the empty list, we can see what's in there. These are the things that are just sort of bookkeeping for the package set, primarily call package, and then this just ways to extend the package set. If we look at bash overlay, it takes self and super, and then it just sticks in bash from, this is a little extension of the inherit syntax. If you put the first thing in parentheses, then rather than inheriting from the current scope, it inherits from the set that you give it. So it's sort of shorthand for, you could also write it as you could write it that way. So if you see inherit with parentheses, it's just rather than inheriting from the current scope, I'm inheriting from that from the set that's named in those parentheses. So what this means is that in my overlay, I'm not actually using self or super. I'm just adding bash from Nix packages because I'm going to need it later, and I don't want to try to bootstrap bash myself. So if I just put the bash overlay in there, hey, look, I have bash now, along with the bookkeeping stuff that was in there. So in the next one, in simple derivation overlay, I actually call that package, the simple derivation package that we defined before. I'll pull that up. So I'm just, with the results of all the overlays, I'm just calling the simple derivation package, and that means that it doesn't matter what order I put these in. Bash overlay, simple overlay. It doesn't matter what order I put these in, it will still get bash from that bash overlay. So if I do that, it works. And if I flip these around and say bash overlay after, I get, not only does it still work, but I actually get the same hash on the derivation, which means that nothing changed and nothing would rebuild. So this is another point. The hashes are not dependent on your Nix source code. They're dependent on what it evaluates to. So if two Nix files are different syntactically or even structurally, but they evaluate to the same derivation, you'll get the same hash and you won't rebuild. Is that clear?
One question I have is about the overlay is seemingly adding something from outside self and super.
Yes.
And is that like considered bad practice, or is that common, or?
I mean, you're going to do that fairly frequently because overlays aren't just, so the reason self exists is to resolve dependencies, which implies that there's something that has dependencies. And the reason super exists is to let you alter the things that are already present. But it's very common to add new derivations to a package set using an overlay. So we're actually doing that a couple different places. We're grabbing bash from Nix packages and sticking it in our own little package set. Just because I didn't want to fill up 6 screens with all the stuff required to bootstrap bash. And then this call package, we're using self.call package because that resolves the dependencies according to what's in self. But we're calling this simple derivation.nix, which again is outside the current package set. So yes, that's standard. Does that answer your question?
Yeah, I think so. But like we're using call package from self, but why would you do that instead of just saying like, I don't know, for that from somewhere else?
So
like,
when I do this, it means that after I apply all the overlays, those are the dependencies that simple derivation will get. So if I somewhere else in here overrode bash to, I don't know, change what version of bash we were using, then without changing anything here, I would get that new version of bash in simple derivation.
But you're supplying bash from somewhere else, but
in a different overlay.
Yeah, different.
Yeah.
Right. So overlays are kind of more contextual.
Overlays are supposed to be a sort of modular way of modular and composable way of altering package sets. And package sets, sort of by their nature, are not ill-foundedly self-referential, but things in the set reference other things in the set. So you don't want to just go in and change something in the set, but then leave all the sort of leave all the pointers and everything else pointing to that in the old set. You want to move everything so everything still references within the same set even after you changed it.
Okay, so when we think overlay, we think like we want to change, we want to override, say, something what's going on, or tweak some process or package set that we want to, that we're
Right.
using. And then,
but it will tweak it both if you're using it directly and also insofar as it's a dependency for everything else.
right, because if other things refer back to it, then it'll be running the overlaid version.
Right.
Okay.
Okay.
Yep.
So the last thing we can do is, I think I need to put this here on the left because if we're folding from the right, we want this to be the last thing. Oh goodness. I'm going to bail out of my REPL and resize my window. This is not Nix REPL being a toddler, but it's Nix REPL still being a little bit difficult. It doesn't handle wrapping very well at all. So load that back in. And so let's take a look at simple derivation message overlay. It expects that in the previously defined overlays, there's already a simple derivation, and it overrides it to pass a different message parameter. So we already saw what happens if we just build simple derivation. We get the Nix is cool message in that file. But if we build that, we get, oh no, that didn't do what we wanted. I need the hash should have changed. So something isn't working because it's not changing my hash. Oh. And again, this is a very simple Nix debugging trick. If you want to know whether what you're changing is actually having any effect, the first thing to do is look at the hash of your derivation and the hash of your output. If they didn't change, then even if you structurally changed your Nix code, it's evaluating to the same thing. Hey, it changed. Okay. So when we're talking about the order of derivations, it goes from left to right. So this one gets applied first, then this one, and the only reason this can get the dependency from this one is because it references self. So from the Nix REPL, we can actually, the :B command, if it's applied to an expression that's a derivation, it'll actually, instead of just putting that derivation in the store, it'll actually build it and print out the output path. So we can go take a look at that output path and, oh look, plow is cool. We overrode that parameter. Put this back over. So does that, I hope that clarifies overlays for people, because I know for me for a long time that was very confusing. When do I use self? When do I use super? It sort of seemed a little bit magical, and I felt like it wasn't very well documented. I know I've gotten quite a few questions about overlays as well, just in the Nix channel.
Yeah, I know that helps me a lot. I mean, I'm not gonna say I'm not gonna ask you any more questions, but I feel like I have a better grounding.
Okay. Does anyone else have questions or feedback? This is the end of the technical material of the talk. I'm just gonna give a couple pointers of where we can, where you can go look for more things after this.
Well, I want to say feedback. It's been very helpful. I think it helped clarify a little nooks and crannies that were confusing. So I really appreciate that.
Okay.
One, I guess, conceptual question is I'm still a little fuzzy. Like, so overlays seem like conceptually useful for overriding behavior and whatever. But so I think like overlay equals override, in my head. But the derivation and package concepts are kind of odd to me. I mean, I generally know what a package is, but where the derivations fit in, like conceptually, I don't have a good sort of first approximate mental model of what I want to do with a derivation necessarily.
A derivation is just an exact description of a very, very exact description of how to build something. Where exactly, absolutely the dependencies and other things are. So that will also, because it's in the Nix store, pin down exactly what the versions are, exactly the steps to take to build it, and exactly where it's going to wind up. So it is that everything fully specified.
Okay, so you don't ever really have a derivation that still takes more input from something else.
If it still takes more input, it's still a package. So you have a package and you keep giving the package input until it comes back and says, hey, I'm a derivation now. That's why.
So package set is kind of more unspecified then. So derivation, you're like, okay, this is it. You know, we're gonna build this thing. Whereas a package set sort of like, well, if I get this thing from here, and if you pass me this, then I can do this other thing. And
well, no, because a package set is actually a set of derivations. It's confusing terminology, but everyone calls them package sets. So I wasn't going to just call them derivation sets just to be novel. But it's not the DRV derivation. It's the Nix expression that if you evaluate it, you'll get the right. But it's
still, there's two derivations, I guess.
It's still fair to call the Nix expression a derivation, because if the Nix expression already pins everything down exactly. The .drv file is just sort of not really compiled, but it's the artifact that comes from that Nix expression that can then be used. So the Nix store command knows nothing about the Nix language. It just slurps up that .drv file and runs bash or whatever else is specified and generates the output.
So what's preventing what is the package set getting us that we couldn't just say, well, why don't we just have a giant derivation that's like the one thing? You know, what is the package? It's kind of a silly question.
The package set is just, again, so first of all, Nix is lazy, right? So just because you have a package set doesn't mean you're going to evaluate all the derivations that are in it, right? So attribute sets are lazy. Just because you evaluated the attribute sets doesn't mean you evaluated their values.
Okay, so one thing that gives you is laziness about everything in there.
Yeah, so it lets, you know, to the degree that the package set is fine-grained, and it's sort of fine-grained to, you know, about the same level that other operating system package managers are, which is to say, we consider this a piece of software, it's bash or it's GCC or whatever, so that exists as an attribute in a package set. So you can be sort of lazy at that level as to what you're building. If you had to build all of Nix packages in order to use any of it, well, they try to. That's what Hydra does. Anytime something changes, it tries to, so that they're constantly building everything, but it's quite a massive use of resources.
Okay.
And we see that too, just because, you know, we're only building like what's necessary to build our executables at Plow, and we still use, you know, we still routinely push up against 500 gigabytes in our Nix store. So.
Okay, great. Yeah, that helps.
Okay. Any other questions? All right. So in conclusion, I'm just going to try to give a couple of pointers, both towards like stuff we could talk about in the future and also where to go independently if you want to learn more. Something we didn't talk about is the module system and Haskell.Nix. So we talked about package sets and overlays, and the Haskell infrastructure in Nix packages is just a package set. And when we were using it, we were using overlays to sort of customize it for what we wanted. Haskell.Nix generates a package set at the end, but rather than using overlays to configure it, it actually uses the module system that was developed to configure Nix OS to configure that package set. So that would be something fun to talk about next time, especially since we use Haskell.nix so often. Relatedly, Nix has very good built-in support for cross-compilation, but that was completely outside the scope of this talk, and we didn't really discuss it at all. The only sort of tangentially related thing was that system attribute for the derivation. We didn't say much about how to debug Nix, which I know I pointed at the REPL, showed Nix instantiate a little bit. I'd love to do another talk building off of what we know here that sort of talks about what if things don't work and how do you figure out what's going on. Is there any, so for my own feedback, is there anything else people think should have been on this slide? Any other things people would like to see future talks on?
Well, I'm not sure what exactly is in modules per se, but probably just some of the basic, diving in a little bit into just what's already in Nix packages. You know, like even to build the Haskell stuff, you need a little bit of whatever GCC and all that. Might be an interesting sort of foray into what do these really look like in the real world.
Right. So sort of a tour through the dark corners of Nix packages.
Yeah, at least some of the basic, like you use bash, you know,
right.
like you're gonna need like a GCC, I don't know, like, you know, use like a BZ, some kind of unzipper compression utility. You know, some of the basic stuff are gonna be there. Also some things like we use some funky stuff like JSON imports, or, you know, we have a stack stuff like, you know, how do those interact with, you know, like how do you open random files and make that part and like integrate that, you know, like, so something about those kind of JSON to Nix expressions or whatever it is that we're doing.
Okay. Anybody else have things that they were hoping to see or would like to see next time?
I don't know. I think that I want to kind of take what I have here and try and do some stuff. I have a couple packages I'll probably try and work on when I'm done with this iPad app stuff. I guess one thing would be also like, I don't know. I mean, I don't know. Like there's other stuff I want to know, but it seems like it's like where I just need to have like a conversation, because like one example is like is bringing foreign libraries in correctly. Like if you need to use a C library in something.
Sure.
But that seems like outside the scope of a talk.
Sure. Anybody else?
Thanks, Edward. I thought this was super helpful. I mean, like, I know that answered a lot of questions for me. I hope everybody else got some stuff out of it.
Yeah, I really appreciate it. I think it was well done, and I learned a lot, so that was great.
Thanks. One thing, this is in the handouts, but I'll just point this out real quick. This last slide here is the sort of the places I found most helpful in trying to bootstrap my own Nix knowledge. A lot of Nix, unfortunately, is use the source loop, but insofar as it's not, the Nix pill series that was originally set up blog posts and is now on the NixOS website. It's good. It's fairly comprehensive. It gets into some corners that, if they are addressed in the documentation, are addressed in really non-obvious places. And it has a very pedagogical structure, so it builds from very little, and just if you need to know something later, it was already discussed earlier. There's a talk by Gabriel Gonzalez on YouTube, Nix Under the Hood. This talks about things like, how does the Nix store work? How does Nix actually build things? It goes over some of the same material about derivations and how they work, but also a lot more practical stuff like how do you copy things between stores, a lot of the sort of the plumbing underlying the Nix store. There are 3 manuals, not counting the Nix Ops manual, which is sort of orthogonal, on the Nix OS website that you'll need to reference for what documentation there is about Nix and Nix packages. The Nix manual documents the expression language and the tools. So tools like Nix instantiate, Nix build, Nix store, Nix shell. The Nix packages manual documents the Nix packages library. It was intended as sort of a developer manual for people who want to contribute to the Nix packages library. So it talks a lot about how things are done, but it also has a lot of documentation of the infrastructure that's there for various languages. So the Python infrastructure is documented there, the Haskell infrastructure, the Rust infrastructure, the LaTeX infrastructure is all discussed in that manual. The Nix OS manual obviously documents Nix OS, but more importantly, from a development side, it documents the module system that was developed to configure Nix OS, but is also used by Haskell.nix. So if you're curious about the module system, which we didn't get to today, that's the place to go look for how does the module system work. This slide's in the handouts, and all of these top-level bullet points are hyperlinked, even though Beamer tries very hard not to tell you that they're hyperlinked. So hopefully that's helpful as you try to dig in further. I'd like to thank Alberto Valverde, who, while he was here at Plow, helped me out quite a bit getting started with Nix. Chris Allen sat through an early version of this presentation, gave me a lot of very helpful feedback. And Scott and Plow Tech, I love getting to use Nix every day, and it was great to have a chance to give this talk. So thank you.
Thanks, Edward. That's good. Yay.
Thanks. Yeah, we should all unmute and clap, right?
Yeah, exactly. Well deserved. All right, man, I want to do this for other stuff. It was really fun. Thanks for all the obvious effort that you put into this, and I think that it really came off well.
Well, thank you. And for future talks, I put the Plow branded Beamer template, as I mentioned in the meeting before, in on GitHub. So that's available for everybody here to use now.
Good deal.
All right. Thanks, everybody.
Thanks.
If anyone has more questions, I'm on Slack, and we'll talk to everybody later.
All right. Bye.